Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We're actually back for part 2 of lesson 8.1. The first part of this lesson dealt with a cool finance application, or at least I thought it was cool. Maybe you did, maybe you didn't. In the second part of this lesson, we're actually going to talk more about the geometry applications and back to more what we're used to. So let's scroll down here, and we're going to start talking about this theorem right here. We actually need to scroll up here to get that vocab word in. Altitude. An altitude is a perpendicular segment drawn from a vertex to the opposite side. So if I have a triangle, any type of triangle, if I pick a vertex and I draw a perpendicular segment, that black line would be an altitude. Now, it doesn't have to be drawn, down. I could draw an altitude here, as long as it was perpendicular. So that black line would also be an altitude. Sometimes altitudes can actually fall outside of triangles. Say I had this triangle right here, and I was drawing an altitude from this vertex up here. That would be the altitude here. You just have to pretend that this other side is being extended. So we're not going to talk about too much about altitudes that fall outside of the triangle. We're going to focus on right triangles today, and all of the altitudes will be drawn inside of the triangle. But again, an altitude can be a segment drawn from any vertex perpendicular to the opposite side. And sometimes you'll have to think about extending that opposite side if the altitude is going to be outside of the triangle. Okay, so now that we know what an altitude is, let's talk about this theorem. The altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So if we take a look at this diagram, our altitude is segment CD. Right, so it's drawn from the vertex opposite the hypotenuse to the hypotenuse. And you'll notice that there's three right triangles created in this diagram. And it just turns out that all three are similar to each other. And this is going to create some cool relationships. It's going to let us solve for different segments and diagrams like this. If we know, which sides are corresponding with each other. So let's go through this proof first, just to show you how all of these triangles are similar to one another. Let's hope I can squeeze it all in. Okay, so I'm given right triangle BCA, that's a large one, with measurement BCA equaling 90 degrees, and the altitude is segment CD. And we need to prove that all three of those triangles are similar to each other. You know what? Pause the video, see if you can fill in most of these statements on your own, and then come back and see how many you got correct. So this first one obviously is given. Then we have CD is perpendicular to BA. Well, that is the definition of an altitude, right? An altitude is going to be perpendicular to the side that it intersects. Definition of an altitude. And then if I know that CD and BA are perpendicular, I know that the measurement of CDB and CDA have to be 90 degrees by the definition of perpendicular. Then I know that CDB, CDA, and BCA are all equal to each other. Well, that's going to be the transitive property of equality. I know that they're all equal to each other because they all equal 90 degrees. We have all those statements up above. Transitive POE. If I know that all three of those angles are equal in measurement, I know that they are all congruent to each other by the definition of congruent angles. definition of congruent angles. So right here, I've proved that I just want to think about what we've proved up to this point, right? This statement is important because I've proved that one angle from each of the triangles is congruent to one angle from all the other triangles. So essentially, we have one set of angles that's proved congruent. Now, I'm saying angle B is congruent to angle B. Well, that should be an easy one. Reflexive property of congruence. And now, I'm ready to prove that two of these triangles are similar. So I have triangle BCA, that is the large one. And let's do lime green BDC. I could do better than that. Okay, so the red triangle and the green triangle, they both have a 90-degree angle. We've already proved that. And they both share angle B. So they have two sets of congruent angles, which means we're going to use AA similarity. Now I'm going to take a look at this other triangle here. Let's do that in blue. This other smaller triangle. Well, the blue and the red share angle A. So again, reflexive POC. And, well, now the red and the blue both share angle A, and they both have right angles, so they are similar by AA similarity. Well, if I know that the red is similar to the green, and the red is similar to the blue, well, then the blue, green, and red must all be similar to each other by the transitive property, I'm going to write the whole thing out, property of similarity. I know we haven't talked about specifically the transitive property of similarity, but hopefully you can see why it's transitive. Right? They're talking about these two statements, these two similarity statements. BCA is similar to both those other ones, so those other ones must be similar to each other, which means all three are similar to each other. So again, this just shows you that when we have that altitude in a right triangle, we end up having three similar triangles. Let's go ahead and look at applying some of this. Now, there are these two corollaries, and they are shortcuts essentially. They're shortcuts for figuring out measurements of different segments when we have these altitude diagrams and right triangles. I'm not going to get too much into them. I put them in your notes because if you want to go take a look at them and you want to try to memorize them, that's fine, right? There are some relationships here that may make it easier in some cases to solve for missing segments. My point is, though, you don't have to understand these to be able to figure out the lengths of segments in these diagrams, right? You can just go back to what we know about similar triangles. So again, these are some shortcuts. You're free to go look at these on your own to try to apply them to the problems we're doing. But I'm going to show you that what we already know about similar triangles and setting up proportions based on, corresponding sides having the same ratios, those are going to work just fine. We're going to do problems 1 and 2. So problem number 1 is you just have to write a similarity statement, but it's for all three triangles. So it's kind of what we did up above in the proof, but diagram looks a little different, letters are different, etc. So see if you can figure out, the order of the letters for all three triangles in that similarity statement. So we need to have, a blue triangle, we'll call that PSR. We'll have a pink triangle, PSQ, and we'll have a lime green triangle, PQR. So our similarity statement, we need to figure out what letters should go where. So pause the video, take time to do that, and then come see if you were correct. Okay, so what I would do is I would relate the large triangle to each of the other ones individually first. So I would start with the green, and I would just pick an order. of letters. So I'm going to start with PRQ. PRQ. Now pick one of the smaller triangles to compare it to. I'm going to start with the pink. Well, let's see. The right angle for the pink is angle S. So that needs to go where the right angle for the green is, which is angle P. So angle P comes first, which means angle S needs to come first for pink. Now, green and pink both share angle Q. So the Q needs to go in the same spot, which is third. And then it's very easy to see that, well, P has to come second. So PRQ is similar to SPQ. Now I'm going to compare the green to the blue. The blue right angle is angle S, so that needs to go in the same spot as angle P. So again, that's going to come first. Blue and green both share R, so the R's need to come second for both. And then the angle that I'm missing for blue is P. And by process of elimination, P is the angle that is congruent to Q. So here's our similarity statement. Again, you could have these written in a different order. Maybe you started, with RQP for green, and then you built your pink and blue off of there. But my point is that start with the large and then compare it individually to both of the smaller ones. That's probably going to be the easiest because it has those reflexive relationships with certain angles that makes it easy to tell which angle should go where. Now we're going to work on number 2. You have to find all 3 variables. What I would do is I would first write another similarity statement. So same idea, come up with a similarity statement, and then see if you can set up the correct ratios. So go ahead, take a few minutes to do that, and then come back and check your work. Okay, so I am going to start with green. Just put that in the middle again. I guess I should have said you may need to label these again because they're not labeled on the diagram. So A, B, C, D. Green, it will go A, D, C. The right angle for green is D. The right angle for pink is B. So those both need to go in the middle. Pink and green share angle A. So those both need to go first. And then D is the one we are missing for pink. So D will go third. For blue, right angle for blue is B, so that's got to go where D is to make it match for green. They both share C, so C is going to go third for both of them, and that leaves us with D to go first. So there's our triangle similarity statement. Now we can work on setting up some of these ratios. There's actually one of these letters that you don't need a ratio for, right? V. Think about why, V is the hypotenuse of a right triangle. So if I want to figure out V, I can just do 3 squared plus 9 squared equals V squared. It's going to give me 9 plus 81 is equal to V squared. 90 is equal to V squared. And it says find exact values, so we can't have a decimal here. I'm going to essentially get V is equal to the square root of 90, which is equal to the square root of 9 times the square root of 10, which is equal to 3 times the square root of 10. So V, 3 times the square root of 10 if we're talking about exact values. Now let's see, what can I set up to find U and W? Well, just, I know all values of the blue triangle. So let's just write a ratio with the blue triangle. And I'll do it in blue to color coordinate. So for the blue triangle, two sides are 3 and 9. Now, let's use the pink triangle. Well, what sides correspond with, or what side corresponds with 3 from the blue? So 3 from the blue is BC. The corresponding side of BC with the pink is going to be BD, which is 9. So 9 corresponds with 3. If I look at the 9 side for the blue, 9 is BD for blue. So BD is in the first 2 spots, which means I'm going to look at the first 2 spots of my pink, which is AB, which is U. Let's do that in pink, though. So this proportion is true based on, corresponding sides. Pretty easy to solve this, right? I get 81 is equal to 3U, which gives me 27 is equal to U. Now it turns out if you wanted, to have a U in your ratio here, because that's the side you were trying to solve for, you may have actually not, it turns out that in another example, right, you may have had to use, side V for blue, right, the 3 times the square root of 10, if that was one of the ones that matched up with U from the pink triangle. In this case, the ones that I chose, 3 and 9, those ended up being the correct sides, but it's possible that, the sides you choose may be the incorrect ones, and you may have to go back and, switch out one of the ones for the other ones based on, what sides are the corresponding ones. You could set up another ratio to find W. However, I think that's going to be more work. I think you should just use Pythagorean theorem again. I think that would make the most sense. Because now I know that U is equal to 27. And now I know 2 sides of my pink triangle. And I can just use Pythagorean theorem. Right, so 9 squared plus 27 squared is equal to W squared. 9 squared is 81. 27 squared, 729. Uh, 729 plus 81 gives us 810. Take the square root of both sides. Is there a perfect square factor for 810? There is. It's 81. So square root of 81 times the square root of 10. Square root of 81 is 9. Oops. So W is equal to 9 times the square root of 10. So again, different ways you could have found these values. You could have used a proportion to figure out what W was, or you could have used the Pythagorean theorem. Whatever is easiest to you is okay. We're going to stop here as far as problems go. Like I said before, if you want to look at those 2 corollaries dealing with the geometric mean, so if you wanted to go look up here, you could try to apply these to the problem we just did, right? Look at what they say, or look at the setups for these, and you could see if that's easier for you. The problem is, what I tend to find is that these are very easily forgotten, right? These relationships. And that's because we just don't work with them that much. They just don't pop up that often, so either we have to go look them up, or, if we're on a test, we'd have to memorize them. And I just find that the brain space that it takes to memorize these generally just isn't worth it. It's much the similarity ratios and the proportions that we come up with, we use those far more often. So those are more ingrained in our heads, which means that we can apply them easier. Even though they may take a bit longer, because we may have to write out that similarity statement, I think we're more likely to get the right answer doing it that way than kind of guessing and, trying to remember what these relationships are. Just because, again, we don't use them very often. So it's up to you. If you want to try to apply these, you can. Just know that you can solve the problems we're doing just using the regular similarity ratios that we've worked with throughout our last unit. Okay, that is going to do it. We are done with this video. Enjoy your day, and we will look forward to seeing you next time.